Hi, the big honor. Today's speaker in the experimental mathematics seminar of Rutgers University is the one and only Neil Sloane, who will talk about new sequences in the recent months. Thank you.
All right, I'll start sharing the screen. Keynote. Share and go to play slideshow. And there's the slideshow. Okay, I'm going to start. Lovely new problems. I've got half a dozen or more interesting sequences. I'm going to go fast because I don't want to be boring. But the slides will be on my homepage very soon. And anyway, the talk will be recorded. Video will be available in a few days, and probably the slides also will be on the Experimental Math website. I'm going to start off by talking about one of the most interesting recent sequences, although I'm not sure it's actually perfect in its present form. But it's a remarkable sequence sent in by Joseph Rozhenko. And it's the kind of sequence, when you see it, you say, boy, I'm not going to do anything else until I've solved this. But I'm already working on half a dozen other sequences that I've dropped everything else to work on. So these are sequences that I would have dropped everything to work on if I wasn't in the middle of working on 6 other sequences that I'm not going to talk about because they're not ready. But this one is really nice. And it starts like this. Let me just tell you the definition. We start off with nothing. We start off with the empty sequence. See the little box here? There's nothing in it. How many zeros do we see in that box? Well, there aren't any. So we see 0 zeros. And that's the beginning of the sequence. It's the first row. The sequence comes in chunks. And when you see a 0, the chunk ends. So we saw a 0, so we start a new chunk. And each time in the chunk, we make an inventory of what we've seen so far. So we start off by saying, how many zeros have we seen so far? Well, there's 1. So we write down a 1. And then we say, how many 1s have we seen so far? Well, you can see 1, 1 there. So we've seen 1, 1. So we write down a 1. And then we say, how many 2s have we seen so far? Well, there aren't any. So we write down a 0. And when we write down a 0, we start a new chunk. Okay, so the next chunk, and we always say, how many zeros? Okay, we've got 2 zeros. How many 1s? We got 2 1s. How many 2s? We've got 2 2s. We just created them. And how many 3s? 0. 0.
It looks a little bit like the look and see sequence.
Yes, it looks a little bit like several sequences, absolutely. It particularly looks like one of Jan van Eyck's sequence, that the Van Eyck, the famous Van Eyck sequence, is a bit similar, but it's actually, when you look at it closely, there's nothing quite like this that I've seen before. So the next row, we start again, and we always ask how many zeros. So we can see 3 zeros, we can see 2 1s, we can see 4 2s, because we had 3 2s already, and we just created another one. And then we've got 1 3, 1 4, and 5 zeros. And the bell rings. It's like a typewriter carriage going back to the beginning, and we start a new row. And it goes 4 4 4 1 4 0, and so on. That's the sequence. And the question is, what happens? Well, this was discussed on the Sequence Fans mailing list, and a lot of my friends got involved and created very nice pictures. Although, even after all these lovely pictures, it's still pretty much a mystery. So here's Jan van Eyck made a plot of the first 1,000 terms, and you can see they go up and down and up and down. This is a literal graph of the whole sequence. The sequence is, you take all the chunks that we've seen and you just string them together. You can think of it as a triangle being read by rows. So it began, you remember it began 0, and then there was a 1 1 0, and then there was a 2 2, what was it, 1 0, and so on. We string all those together. That is the sequence. So it starts off with lots of little numbers, and the numbers get bigger and bigger. After 1,000 terms, Jan van Eyck noticed that there's an envelope, which is the inverse triangular numbers. It's roughly a square root of 2n. And the wobbles go up and down, and they just touch that. However, when he went to 10,000 terms, that brown curve got swamped, and that was no longer the solution. So it's not that simple. And in fact, it's really not that simple at all. Here's a graph of 10 million terms that Remy Segrist created. And this is really astonishing. Usually, when you plot one of these sequences, you see lines, trajectories that sort of spray out from the start, and they very rarely cross. This one has lines that cross in a really amazing manner. Look at this line down here, which seems to cross through all the other tracks. What's going on? We don't know. We can look at various parameters. We can look at the lengths of the rows, and this is what they look like. Well, all right, they're increasing, but in a kind of a staccato, peculiar way. You can look at when K first appears, and you get a rather messy thing. And what about the rows themselves? For a while, I thought it would be nice to listen to this, and I was going to get it set up so I would play the sequence on the grand piano, which sounds pretty good because each row is a chunk. And keeping in mind, say, Beethoven's Diabelli variations, here we have the variations, but we don't know what the Diabelli theme is. And it may be that that's actually thinking about it, preparing the stalk. That's really not the way to look at it. I think one needs to look at it from a differential equation a point of view. And I actually think the definition is slightly wrong. The definition stops when you get to a zero. I don't think that's right. I think the definition of a row, you should keep going until you've exhausted everything you've seen so far. There are some cases, so I think there should be another version of the sequence, which I was in the process of doing when I noticed that my talk was about to begin. So I gave up. But if someone would like to do this, it would be really interesting. And I can explain more if you send me email. All right, that's the end of the first chunk. The second chunk, last time I talked here a year ago, I'd been working very hard with Lars Blomberg and Shannon. God, I know so many people called Shannon. Forgive me. Bloomberg, Shannon, and Sloane. There's a paper that's going to appear in Integers in the Scott Shannon. Sorry, Scott. Forgive me. Lars Bloomberg, Scott Shannon, and myself, we have a paper that's going to appear in a special issue of Integers in honor of Ron Graham, in memory of Ron Graham. And we look at various stained glass windows problems. The classical one is an old paper of Bjorn Poonen and Michael Rubenstein, who I will just call P and R. They solved the following problem. Take an n-gon, a regular n-gon. Here's a regular 23 gon. It's got 23 equally spaced points around a circle. Join every pair of points by a chord, and you get a lot of little cells, and you get a lot of little points in between. They worked out an explicit formula for the number of cells and the number of points in this picture. And we've been, our motto in this work is, if you can't solve it, make art. So this was solved already, but we still made art out of this. We colored it very nicely. And I should say that their formulas are much simpler if n is odd, because when n is odd, you only ever get simple intersections here. When n is even, you can have places where more than two lines meet, and that makes the counting far more difficult. If you want to see more pictures like this, go to sequence A7678. Scott, earlier this year, Scott Shannon said, what happens if you extend all the chords to infinity? So here's an example. The white dots are the original hexagon that P and R studied and solved. They found out how many regions there are in the hexagon. Scott says, let's extend all the chords to infinity and let's count the regions. Let's only count polygons, well-defined polygons. Let's ignore the polygons, the non-polygons that go off to infinity. So we just count the finite polygons. And you can see here the total number of polygons. There are 36 triangles. There are 18 new ones. Around each edge, we've added 3 triangles. So we have the 18 original triangles inside that P and R enumerated, plus 18 new ones. So there is a total of 36 triangles now. The number of quadrilaterals is still the same, it's 6. So we have 36 triangles, 6 quadrilaterals, 42 polygons. So that is the 6th term of Scott's new sequence. It's A344857. If you go to 7, a polygon, the white dots are the 7 gone that P and R analyzed, but now we have extra cells, we have extra quadrilaterals and extra triangles, and plus the original stuff inside. Total is 99 polygons. So we have a sequence. If I hit down, why is this frozen? I don't know. It was just slow to respond. Okay, so here's the sequence. It's the number of polygons in a drawing of the complete graph on n nodes with all the chords extended to infinity. And I showed you this, the term for n equals 6 is 42, for 7 it's 99. Here's the sequence. Scott worked out 100 terms, and he guessed a formula if n is odd, which is a 4th degree polynomial, and so far we don't have a proof, but I suspect proving this won't be too difficult using the methods of Poonen and Rubinstein. But for n even, we don't have a guess, and that may be a bit more complicated. I tried doing an obvious thing. Can you invert in the polygon and make all the outside ones on the inside? But that didn't work. So anyway, here's the sequence. We have 100 terms, and we only have a guess for the odd indexed terms. Another thing we looked at, and this is where we really had to create art because we couldn't solve it. Instead of looking at a polygon, take a grid of squares. So here's a 3 by 3 grid of squares. Look at all the boundary points and join every pair of boundary points by a chord. So that gives you a graph, a planar graph with a lot of cells and a lot of interior points. And we can work out what happens here. We cannot solve this in general. The name of this graph is BCMN. This is BC33, meaning take a 3 by 3 block of squares, join all the boundary points. BC means boundary chords. And if you look, excuse me, if you look at sequence A3331, sequence A331452 has many more beautiful pictures like this, and some formulas, not many. There's one case where it's been solved. If you look at BC14 or BC1N, BC14 means take a strip of 4 rectangles and join all the boundary points by lines. So here's BC14. If you look at this, you see there are 104 little cells. There are 70 triangles and 34 quadrilaterals. There are no pentagons. There are no hexagons. And Max Alexeyev proved that when you look at BC1N, there are never any cells with more than 4 sides. But his proof was kind of indirect because it's based on a theorem, a Russian theorem, I have to say, about training sets for threshold functions. And it seems to me there should be a simple geometric proof that when you're doing this, you can imagine walking down the sidewalk with square tiles, join all the points by lines. Why do you never see a pentagon? Open question, need a geometric proof. All right. I mentioned this a year ago, and it's still open. Another question, also from a year ago. Let's look at the interior nodes that are simple. So I've gone back to BC12. This is very simple. A 1 by 2, 2 squares side by side, join all the boundary points by lines. How many simple intersections are there? Well, there's one point which is not simple. This point in the middle has 3 lines through it. That's not a simple point. All the others have 2 lines through them. So there are 6 interior simple points. So this is the sequence. This is the tooth, the second term for the 1 by 2, 334701, 6 interior points. For this sequence, we have 500 terms, and we do not have a formula. This is really annoying. It's a simple question. Count the interior point in simple interior points in a strip of squares. And 500 terms, no formula. And I have to say this happens far too often working in sequences. Very often we end up with a sequence of hundreds of terms, simple definition, and no formula. So I was talking to Mark Lebrun the other day, and he was saying, you know, we really ought to do something about this. We could strengthen SuperSeeker. I have this program called SuperSeeker that you give it a sequence, and it tries very hard to find a formula. It runs GFun, it runs all kinds of programs, and it keeps looking up the intermediate results in the OEIS. So it has the whole of the 350,000 sequences in the OEIS at its disposal. And if one thing it doesn't do is take your sequence and try to express it as a linear combination of 2 sequences to existing sequences. But that's just one possibility. There are a lot of extra things we could do. So Mark was saying, if we had a small group of volunteers, interns, you know, who could just to help with this occasionally. So if you're interested in helping strengthen SuperSeeker, maybe using some, you know, artificial intelligence ideas, we need volunteers. If you're interested in helping, send me an email or send an email to Mark Lebrun. Okay, I will get on to the next topic. The next 2 sequences seem totally impossible. And actually one of them is still impossible. The second one, actually, we've made a bit of progress. Not me, but the world has made some progress. The first one is Stan Wagon has these occasional problems of the week. This is, I think, from March of this year, problem of the week 1321. And he says, listen to this question. You can pick a set of n different numbers. That's the only constraint. They don't have to be, they're integers, but they can be negative. And what you do is you look at the sums of 2 of them, sums of pairs of distinct elements in S. So n choose 2 sums. And you're only interested in cases where the sum is a power of 2. If it's not a power of 2, forget it. So, and then Wn, I called it W of n for Stan Wagon. It's the maximum that you can get, the maximum number of sums of pairs of 2 with n starting numbers. So for example, the one case where you can solve, well, you can solve W equals 2. It's trivial. But W3, we want 3 numbers such that the sums in pairs are powers of 2. So take -1, 3, and 5, and you get -1 plus 3 is 2, good. -1 plus 5 is 4, good. 3 plus 5 is 8. So we've gotten 3 powers of 2, 2, 4, and 8. And those don't have to be distinct. And the question is, what's the most you can get? Well, with 3 numbers, you can't get more than 3. 3 choose 2 is 3. So this is optimal. And this is the only case we know the exact solution, although we suspect we have good guesses for n up to 100. But even for W of 4. With W of 4, you can get 4 powers of 2 by taking -3, -1, 5, and 3 and 5. You can get 6 from -1, -3, -1, 3, 5, and 11. And you can get 15 from this set. The original problem that Stan stated, he had a set of 10 numbers that gave 14 powers of 2. And he challenged people to find a bigger number. And quite a number of people solved that problem by finding that you could get 15. And in his solution, he announced that, in fact, Rob Pratt had proved that was optimal. But it turns out that wasn't quite true. That was a bit of a disappointment. I wrote to Rob and said, how on earth did you solve this? And he said, actually, I didn't solve it. What all I did was to use mixed integer linear programming, making some assumptions about the range of these numbers. And he picked the range. He said, let's restrict ourselves to a set S where the numbers, we've got n numbers in the range minus n plus 3 to plus n plus 3. That's a pretty good range. He ran his linear programming on that for the first 100 terms, and he got a sequence which looks like this, and it actually matches everything we know up to 100 except for n equals 5. For n equals 5, this only gives 5 powers of 2 from this set, whereas, as I showed you on the previous slide, you can actually get 6 by using this, expanding the range. You need an 11 in there to get 6, but still. Now, what about bounds? In Stan's follow-up to this, he said that there was an upper bound by Peter Zielinski of big O of n times log n squared. But I think, again, that was assuming that the numbers were bounded to some range. I don't think we have an upper bound, other than the obvious trivial bound of n choose 2. What about a lower bound? So this is from Stan's solution page to this. He said, it looks like a very good thing to do is to take an arithmetic progression of increasing by 2 each time, pick some m. You're going to adjust m to get the best you can. Go from m minus m up in steps of 2 up to m plus n minus 2. So for example, if you take 16 numbers and you take m to be 5, you go from minus 11 up to 19, and you get 29 sums that are powers of 2, which I've written out here just to emphasize that the powers of 2 don't have to be distinct. So this arithmetic progression gives you 29 as a lower bound for n equals 16. And in general, it gives you big O of n log n as a lower bound. So certainly a lower bound on W of n, and it may actually be pretty close to the truth. We don't know. So that was the end of the second impossible problem. The second, I mean, that was the end of the first impossible problem. The second impossible problem is the stepping stones puzzle. So this was invented by 2 undergraduates from Michigan in October of a year ago. And the game goes like this. It's a puzzle, and you play it on the square grid. You put down stones on a square grid, and you start off, you've got 2 stones that are labeled 1, and you can put them anywhere you want, which is why this sounds impossible. You can put them anywhere at all on the square grid. And then you want to put down more stones that have numbers on them, 2, 3, 4, 5, as high as you can go. And the rule is you can put a stone down with a 2 on it. You've got to go in order, a 2, a 3, a 4. You can only put a 2 if the sum of its 8 neighbors is 2. Each stone has 8 neighbors. If we separate the 2 ones by a gap of 1, then we can put a 2 down here because it's got 2 neighbors, 1 and 1, that add up to 2. So it's legal to put the 2 there. And then once we've done that, we can put the 3 here because it's got 2 neighbors, 1 and 2. So now we have 1, 2, and 3, and a 1 here. And then we can put a 4 here because we've got 1 and 3. And then we can put a 5 here, and 6, and so on. And after a while, you get up to 16. And they proved that you can't do more than 16, starting with 2 1s. And that's the puzzle, that's the sequence, 3, 3, 7, 6, 6, 3. And 6 values are known. It really does sound impossible, but with some clever programming, people have found the first 6 values. And we have upper and lower bounds. And there's a really lovely lower bound that Andrew Halroyd found that goes like this. You start off with 2 1s with a gap between them where you can put a 2. Once you put the 2 there, you can put a 3 and a 4 and a 5 and a 6 there. And then if you put the next 2 away, you can put a 7 there, and you get a 7, an 8, a 9, 10, and 11. And then if you put the next one there, you can get a 12, 13, up to, and then you zigzag. and that gives you 5n minus 4. Very nice lower bound construction. What about an upper bound? Well, this also is pretty clever, pretty nice. Robert Gabish proved, first of all, he proved an upper bound of n log n, and then by some clever trickery, he improved it to a linear bound of 714 times n. But let me show you how his argument goes. You say, suppose we have a really big number. Suppose we've been very clever, and for all we know at this point, it maybe you could get as big a number as you want, starting off with 3 stones. Then maybe there's no limit. Well, there is a limit, and here's why there's a limit. Suppose you have a high point of k. Then how did you get that k? It must be the sum of 2 of the 8 neighbors, 2 or more of the 8 neighbors. Now maybe there's a 1, maybe there's a 2 or something, but you know at least there has to be a neighbor which is at most k over 2. If we see a 16 here, then at least around it there has to be an 8 or less. Otherwise you couldn't get 16 as a sum of its neighbors. Okay, so then look at the k over 2. Say it was k over 2. Look at the biggest neighbor. I mean, the biggest, smallest neighbor. Okay, there has to be a k over 2 or less. Look at its neighbors, and we can say that the neighbor of this is at most, there has to be a neighbor which is at most k over 4. And that would be 2 steps away from k. And there has to be a neighbor at least at most k over 8, 3 steps away. And if k was around 2 to the d plus 1, there has to be a square within distance d of s containing a number which is at most this number divided by 2 d times. In other words, 1. So to summarize it, if we look at the starting square that had the k in it here, then there's a 1 within distance d of it, if this is just under 2 to the d plus 1. Well, this 1 is surrounded, it has its territory. The numbers that are within distance d of it are within a square of size 2d plus 1. Okay, let's look at this. And let me convince you that really you can't get too big a number here. Suppose we had a high point. I was going to put Everest here, but it's a little bit easier to double the height roughly. So we put here 65530, just under 2 to the 16. By this halving argument, there has to be a 1 within distance 15 of it. So think of this as a mountain peak and the 1s as climbers' huts. Okay, so now let's look at the picture. We've got, let's say we had 3 1s, 3 huts, and each hut is surrounded by a square of size 31 by 31, so that's just under 1,000. So these 3 huts total cover at most 3,000 squares. On the other hand, they've been able to get up to 65530. That means someone has put down stepping stones, 2, 3, 4, 5, 6, all the way up to 65529 before this. So inside these squares, we must have all the numbers from 1 to 65530. But the total area here is at most 3,000. So that's a contradiction. So it's bounded. And so the upper bound, that's how, with more clever counting, Robert Gabish gets 714 times n. And here are 2 more examples showing what we know. Clever trickery, and the entry 337 has lots of detail about the programs. And this is and links to the Code Golf website. I'll have a drink of water. Are there any questions? This is a new.
Why is it that you have to stay inside of those boxes in the previous sequence? Why couldn't we have exited the boxes and then come back?
Yeah, I don't know. I'm not sure. Good question. I don't know. Look at his proof in the entry. Actually, I don't think you can leave them. All right. So the next topic is a new L.E.S sequence. L.E.S sequences are lexicographically earliest infinite sequences. And what do we mean by lexicographic ordering? Well, we put all the sequences, all right, lexicographic order. We arrange all the infinite sequences of integers in lexicographic order. So 1, 2, 3 comes before 1, 2, 4, and so on. So this class of sequences is defined in the following way. You always follow the pattern. You ask for the lexicographically earliest infinite sequence of distinct positive numbers with some property. The classic example is the EKG sequence, where each term has to have a common factor with the previous term. The GCD of the nth term, you pick it usually to be the smallest number that has a common factor with the previous term. That's sequence A64413, and it's pretty easy to prove that you get every number. The definition requires that the numbers are distinct, but there might be missing numbers. And the tricky part is always to prove there's nothing missing. So the EKG sequence, you can prove without too much difficulty that there's nothing missing. Then a variation on that is the Yellowstone permutation. The EKG sequence is called EKG because the beginning looks like an electroencephalogram of your heart. It goes up and down in a slightly irregular way. The next one is the Yellowstone sequence. And now the rule is you've got to have a common factor with the term 2 back. So the GCD of the number you're looking for, A of n, has to be, with A of n minus 2, has to be bigger than 1, but the GCD with the previous term has to be 1. And that's A98550, and that erupts every so often. You get a big spike. That's why it's called the Yellowstone permutation. There's a geyser that appears, and again, you can prove that it's that every number appears. It's a permutation of the positive integers. Yes. The Enots Wolley sequence. This was a contribution from an idea of Scott Shannon. He said, what if we switch these two conditions? Instead of having, okay, so now the condition is it's got to be relatively prime to the term that's 2 earlier, and it's got to have a common factor bigger than 1 with the previous term. So we just switched them. That's why it's called Enots Wolley. You might think Enots Wolley is the name of some old geezer. It's a very Australian sounding name, and Scott lives in Melbourne, and I used to live in Melbourne. Enots Wolley is a very Australian sounding name. And but in fact, it's, as you can tell, it's Yellowstone backwards. And is it a permutation of the positive numbers? We just don't know. We know a lot about it, but it's a gap. I wish somebody would solve that. I was going to offer a large amount of money, but I don't know. I decided not to. But please, would somebody kindly solve that? Well, the new sequence is in the same spirit, but I think it's actually going to be harder. So Grant Olson submitted this last month, and the rule here is it's the lexicographically earliest sequence of distinct positive numbers such that the GCD of the new term with the previous term plus 1 is bigger than 1. But you may not take the next term to be the previous term plus 1. Okay, you cannot do the obvious thing. So if we start with 1, the rule says, all right, add 1 to that and we get 2. The next term has to have a common factor with 2, but it may not be 2. So it's got to be an even number that we haven't seen. And so 4 works. so it has to be 4. Okay. What's the next term? Well, 4 plus 1 is 5. The next term has to have a common factor with 5, but it may not be 5. And since 5 is a prime, there's really nothing you can do. The next term has to be twice the prime, twice the previous term plus 1. So it goes 1, 4, 10. Now, 10 plus 1 is 11, so we get 22. 22 plus 1 is 23. It's got to be 46. 46 plus 1 is a 47, a prime, so we've got to be 94. So we've shot up by doubling 3 times in a row, 4 times in a row, basically, and we've gotten up to 94. Now, when we add 1, we've got 95, and we need the smallest number, which has a common factor with 95 that hasn't been used. Well, now we can bring in 5 that's been waiting around, and then 2, and so on. And the problem is to show this as a permutation of the positive numbers. And the reason I think this might be hard is that if you look at a graph of this, it looks even more irregular than the Yellowstone permutation. At 94, 95, there's a huge jump. And the reason for that is that when we're chugging along, most of the time, A of n is pretty close to n. When we get to 87, the 87th term is 81. Add 1 and we get 82. We need a common factor with 82. Well, any even number would count, and there's an even number that hasn't been used, 88. So the 88th term is 88. Add 1 and we get 89, which is a prime. So the next term is double it. Add 1 and we get 179, which is also a prime. And we get another prime and another prime and another prime. This is what's called a Cunningham chain of primes. Each prime is twice the previous prime plus 1. And that's what created that large eruption at 93, 94. And because these Cunningham chains are pretty mysterious, this is the kind of thing like the kind of prime number problem, which there are conjectures, but it's very hard to prove anything or even to really know what's happening. I don't think I think it's an open question about how long a Cunningham chain can be. So if that can't be solved, that's going to presumably make this sequence pretty hard to solve. And
Neil, how come we didn't have this issue in the previous sequences?
Because the main difference is we've added 1 to the previous term before we act on it. And so the primes that we had around earlier sort of disappear. When you add 1, the prime structure just totally changes. And that wasn't true for the earlier sequences. They were much closer. The terms were much more closely related.
Yeah, so it's probably impossible.
It's probably impossible, yes. Yeah. I can prove that every prime divides infinitely many terms in the sequence, but that's all. That follows from the standard kind of EKG argument. But I can't prove that every prime appears naked in the sequence.
Okay.
Another thing is there are set theory versions of these sequences. Of this set theory meaning we're looking at sets of integers. And to explain that, let me tell you what it means. I'm going to talk about binary expansions of numbers. The binary expansion of 5 is 101, and of 10 it's 1010. Those two binary expansions are disjoint in the sense there's no place where they have a 1 in the same place. Whereas 6 and 10 do, 6 and 10 have a 1 in the same place. So 6 and 10 intersect, 5 and 10 don't intersect, they're disjoint. So the set theory analog of the EKG sequence is, the rule is A of n is the smallest number you haven't used that intersects the previous number. So and we start with 1, all right? So we want a number that intersects 1 and is the smallest possible. So 3 works. because 3 is 1, 1, and those two ones intersect. So it begins 1, 3. And then we need the smallest number that intersects 1, 1 that we haven't used, and 2 works. And we get 1, 3, 2, 6, 4, 5, 7, 9, 8. And then it goes 10, 11, 12, 13, 14, 15. And then at the next power of 2, we get 17 and 16. But apart from that, basically the nth term here is n. So it's very easy to prove that every number appears. Now, when we do the same thing for the Yellowstone, it is very difficult, it turns out, surprisingly difficult. We know that the ordinary version of the Yellowstone is a permutation. Every number appears. When you look at the set theory version, it goes 1, 2, 3, 5, 10, 4, 8, and we have not been able to prove that every number appears. And this has been around for a while, sequence 252867. I wish somebody would solve this one too. Let me show you a graph of the first million terms. Now, if you look at the first million terms of the set theory version of the EKG sequence, it's a dead straight line with a few little twiddles. It's basically the line y equals x. This is totally mind-boggling. This is a graph of that sequence. The red lines are powers of 2. This does not look like a permutation, does it? But it seems that it is. All right, gerrymandering. A topic that's been in the news in the past few years for political reasons. We have a couple of sequences that were sent in by Shawnee and Don Rebel, dealing with a very basic, simple-minded version of the gerrymandering question. Let me show you, let me go to the next picture, and then I'll come back to that and tell you what the rules are. So we've got a town with 36 voters, and 22 of them vote for candidate A. So these are the A voters, and there are only 14 B voters, and they're there. But the rules say whoever wins the most districts wins the election. So if you cleverly divided up the regions into 3 groups of 12, then even though B has only got 14 votes, B can win the election because he wins. We've divided up the 36 cells into 3 districts of 12. And by drawing the electoral districts like this, B gets 7 out of 12 here and wins this district. B gets 7 out of 12 here and wins this district, and the other district it gives up on, but it wins 2 out of the 3 districts, so it wins the election. And then and 14 is the minimum number of votes so with the rules. Let me go back to the rules. The rules are, you've got 2 candidates, you've got n voters. The voters are divided up into D equal districts of size n over D. And the districts are winner take all. Tied districts don't go to either candidate. And if there's an even number of districts, you can win. It's enough if you win half the districts and tie in 1 further district. And the answer depends on the divisors of n, but the minimal number ranges between, I think it's n over 4 and n over 2, depending on the factorization of n. So, and these 2 sequences. So there's been quite a bit of news recently about work on gerrymandering, and Moon Duchin at Tufts University has a group studying this question. The group's called Metric Geometry and Gerrymandering Group, and there are many papers. If you search on the archive, you'll see a large number of papers. There's one, for example, from 2018 called Gerrymandering Metrics, how to measure what's the baseline. It seems to me we should have more sequences in the OEIS based on other ways of measuring gerrymandering. While I was going through this preparing this talk, I noticed that a lot of my friends were mentioned in this. So I just want to say it's a great privilege to be working with these people. These are people whose names I see every day. So thank you. I have one last slide just to mention that 4 days ago, there was a new theorem that exists because of the OEIS, and the theorem has to do with partitions. And the theorem says that two sequences are equal. One is the number of partitions of n into distinct parts with the property that the difference between the greatest part and the least part is equal to the number of parts. And the other is the maximum number of parts in any partition into distinct parts minus the number of ways to partition n into consecutive parts. This is now a theorem. It was conjectured by Omar Pole, and there were two independent proofs by William Keith and Roland Bacher, and Don Rebel just sent me a rather simpler version. So
Conventional time is 50 minutes.
there are many other opportunities for proving theorems, because all you have to do is look in the OEIS for statements that it appears that, or it is conjectured that, and so on. So I'll stop there.
Let's thank Neil. Please unmute yourself. We have 2 minutes for formal questions, and after that, we'll stop recording, but people are welcome to stay and ask Neil or each other informal questions. So I have a quick question regarding this guessing a polynomial, the sequence that you have it for even n. Do you know that there is no quasi-polynomial that fits the data?
No, I don't know that. No, it's a good question. Yeah, I suspect that there is, but it must be very complicated with a lot of different escape clauses.
Yeah, it's fascinating.
Similar to the solution to the original polygon question, where the formula asks if there's a contribution to the term if n is divisible by 12, there's a contribution if n is divisible by 24, and so on. So it's a sum of it's like a weighted sum of terms.
Other quick questions?
Yeah, I got a question about Stan Wagon's sequence. Has anybody looked at slight modification, one where you require all the numbers to be positive, so you can't use -1, for example, and other, what about s plus t, not a power 2, but a power 2 minus 1?
I don't know. What I would do is work out the first few terms and look it up in the obvious place. That would, if it's a known problem, hopefully that would give you a pointer. I don't know.
You see that a power 2 minus 1 makes it into a set theory problem.
Yes. Yeah. Right.
Well, this ends the formal part of the talk. Robert, please stop recording, and people are welcome to stay and ask informal questions.